Inversion means to turn upside down, like what happens to you in a roller coaster. Matrices can't write them, but they do have other things like determinants, adjoint, and singular or non-singular matrices that can help them do the same work. We have been teaching you these things because we were preparing you for something that will require the use of all these terminologies and methods. That is the inverse of a matrix. So, let's explore one of the ways to find it, that is by using the adjoint. During this, you will see everything you have learned so far being put to use. Let's get started. First of all, take a look at the formula. I'll leave it written here for reference. If M is a square matrix, then the inverse of M is given as the adjoint of M divided by the determinant of M. If M is A, B, C, D, then its adjoint is obtained by interchanging the diagonal entries and changing the signs of other entries. The determinant can be found by the cross multiplication of these two minus these two, that is AD minus BC. But it should be a non-zero, that is non-singular. Why? Because we can't put 0 in the denominator down there, as anything upon 0 is undefined in mathematics. That is why we can only find the inverse of non-singular matrices. Let's start solving an example. Here we have a 2 by 2 matrix A. I am going to find its inverse, and we have already discussed the formula. To use it, we need to find the adjoint and the determinant of A. However, you should always find the determinant first, because if it is 0, then the inverse cannot be calculated, and we stop right there, which saves us a lot of time. Here the determinant of A will be 2 into negative 3 minus 1 into negative 1, and it gives us negative 5. This is not equal to 0, hence the matrix A is non-singular, so we can continue finding the inverse. For the adjoint, take matrix A again, swipe the diagonal entries and change the signs of the other entries. Now that we have both the determinant and the adjoint, put them in the formula. This negative 5 down here divides the whole matrix, which means that it will divide every individual term of this matrix above it. After placing negative 5 under every number, we can see that no number is further divisible and decimal values are undesirable. So we leave them as they are. This is your final matrix, which is representing the inverse of A. But how can we be sure that this matrix is actually the multiplicative inverse and not just any matrix with some random numbers? Remember this relation? A into A inverse equals A inverse into A equals I. We can use it to verify our claim. Just focus on this. A into A inverse equals to I part. If the matrix that we found is actually the inverse of A, then A by the inverse of A should return a unit matrix. Let's see. We have A over here and the inverse of A over here. Multiply first row with first column, first row with second column, second row with first column, and finally second row with second column. Solve the fractions and you will get 1, 0, 0, 1, which is in fact an identity matrix. By verifying the relationship, we have checked that this matrix was actually the inverse of A. In this lesson, you learned to find the multiplicative inverse of a square matrix by using its adjoint. You also learned how to check if the result is correct. That is all for this lesson. We'll see you in the next one.